Trigonometry, Chapter 7, Applications of Trigonometry, Vectors, Section 1, Oblique Triangles and the Law of Sines, Video 6, The Problem with Using the Law of Sines to Find an Angle. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous videos, we solved some problems using the law of sines, and in each, we knew two angles and one side. Don't believe me? Go back and watch the videos again. In this video, we explore what happens when we try to use the law of sines to find a missing angle. Think about it. If you're given two sides and an angle, excuse me, two angles and a side, you can always find the third angle pretty straightforward. But what happens if you're only given one angle and two sides and you want to find a missing angle? For example, in triangle ABC, no picture provided, suppose angle A is 55.3 degrees, side A is 22.8 feet, and side B is 24.9 feet. Find angle B. Well, this seems straightforward enough. We have the complete angle side pair for the A's. We know both side A and angle A, and half of the pair for the B's. So we can directly set up the following law of sines. Sine of A over A, sine of 55.3 degrees over 22.8 equals sine of B over B, or sine of B over 24.9. So let's solve this. Let's multiply both sides by 24.9. And notice I didn't say cross multiply. The reason I didn't say cross multiply is that I'm trying to solve for B. If I want to solve for B, I need to get rid of the 24.9 and then the sign. If I cross multiply, I'll get rid of the 24.9, but then pick up the 22.8. Cross multiplying is cute, but when you're solving an equation, you should focus on getting rid of the things that are preventing you from knowing the solution. In this case, the 24.9 and the sign attached to the B. So we're going to multiply both sides by 24.9. That'll make it show up in the numerator on the left side of the equation. And then to get rid of the sign, we just do sine inverse or inverse sine. And so B is sine inverse of that expression. If we put that in a calculator, we're going to get about 63.9 degrees. Go back and pause the video and put that in just to make sure that you're capable of putting this into your calculator. But we get about 63.9 degrees. So what's the problem with this? Well, the problem is that's not the triangle I had in mind. This is where angle B is actually 116.1 degrees. Everything else is the same. How do I know that's the correct angle? Well, use the law of sines. Hit the law of sines on this picture. Put sine of B over B, sine of A over A, and you'll see that they're equal to each other. So what's wrong with the 63.9 degrees? How do we get it? Well, nothing went wrong. Nothing went wrong at all. Law of sines will verify that this triangle works with the angle that I wanted, but the equation produced this. And here's why it went a little bit off the rails. The answer into what went wrong lies in when we took the inverse sine. In other words, when we did this move here, when we went from here to here. That's not a wrong move, but it opens up some possibilities. As a function, inverse sine, its range is negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. And since our angle is in a triangle, inverse sine can only return acute angles from this range. It won't return a negative angle because our triangle won't have a negative angle. So it can only give something between 0 and 90. So let's go back to where we actually took inverse sine. And for the sake of clarity, I'm going to evaluate this numerical expression on the left. Put it into my calculator on my iPhone, and these are all the digits that it showed me. Sine of B equals this rather long decimal number. Now, as a trig equation, and this is where it gets a little bit more theoretical, but as a trig equation, let me get my pen up. The solutions to sine of an angle equal a positive number are in two quadrants. Think cast. Sine is positive in quadrant 1 and quadrant 2. Sine inverse can only give me an answer here. There's also a solution to this equation in quadrant 2. The inverse sine can only give me the 63.9 degrees. But if you put that as a reference angle in quadrant 2, in other words, if you put 63.9 degrees right here and then measure it from standard position, you get the 116.1 degrees, which now begs the question, how do you know which angle to use? Are there always two such angles? And the answer is, it depends. Sometimes there are two solutions. Sometimes there's just one solution, and sometimes there's no solutions. So when you're using the law of sines to find an angle, it's not just do the math and get an answer. It's do the math and be aware that there may be two solutions, one solution, or no solutions. Now, in the next video, we will disambiguate these different scenarios that can arise when using the law of sines to find an angle. But at the very end, the summary is going to be keep in mind that there's two angles and see which, if any of them, work. By the way, here's the two triangles that satisfy the given criteria. This one is the triangle that I had earlier, right there, just kind of at a different perspective. And here's the one that has the 63.9 degrees. If you want to pause the video and check, you can see that they have the same angle A, side A, and side B, but different angle Bs. But you can hit both with the law of sines to see that they are valid triangles.